Thank you very much for coming. I'm excited to introduce some of you, if you're not familiar, with the field of haptics, which means anything having to do with the sense of touch. And the talks we heard this morning were a great introduction to thinking about media and sense-making. This talk is going to be much more literal about sense-making. How do we recreate a sense, the sense of touch, using artificial means, and what does that mean for people, interaction with computers and robots, and where is this field going in the future? So to start, let me just give a basic definition. Like I said, haptics means anything having to do with the sense of touch, but touch is very complicated, and while this division here between cutaneous or skin-based information and over here kinesthesia or force and motion-based information, touch isn't really like that. It's not a strict division, but sometimes we need to create categories in order to make sense of the world. So that's what we do with the sense of touch. This cutaneous side has to do with sensing in your skin. If you feel that something is hot or cold, or you run your finger over your chair and you feel a texture, these are things that you sense in your skin with tiny sensors called mechanoreceptors. That's on this side. Over here we have kinesthesia, which has to do with large-scale motions and forces on your body. If I push on this chair and I feel how hard it is and the fact that it's supporting the weight of my body, that's kinesthesia. In addition, just knowing where your body is in space is part of kinesthesia. So we'll do a little audience participation now. Everybody can hold their hands over their head like this, and don't look at your fingers, but point them upwards. Point your fingers toward each other and then try to touch them together. So if you're like me, you miss the first time, and then you can recorrect. And that little demonstration was just to also show you some of the limitations of the human sense of touch, in particular the kinesthesia, which is supposed to tell you where your body is in space. And we don't do this perfectly. Without looking at our hands, we don't know exactly where they are, although we can get pretty close. It's the combination of kinesthesia that gets our hands to be in the general area where they need to be, and then the cutaneous information of making that contact and feeling the skin-to-skin touch that takes us the rest of the way. And so it's the combination of cutaneous and kinesthetic information that comes together. It lets us coordinate our movement and also enable perception of the world around us. So this is key to sense-making, especially in certain populations who lose the sense of touch. So of course you can imagine someone who is missing a limb and has a prosthesis. This person is losing the sense of touch in the most fundamental way because they've lost their limb, and so no longer have the sensing apparatus. And so one area of technology development, of course, is how do you give someone like this an artificial sense of touch? However, we're not just limited to special patient populations who lose the sense of touch. There are many skilled, challenging tasks that we would like to do in the world where experts will lose their sense of touch. So here's an example of someone teleoperating the Canadarm with a big dexterous manipulator on the end at the space station. In fact, this arm can sometimes go on the space station. There's also versions that go on the space shuttle. I know this one's on the space station because the space shuttle's hanging out in the background there. And the idea is that an astronaut, instead of doing a spacewalk, would like to stay within the safety confines of the space station and teleoperate this giant robot outside the space station in order to do repairs, to do experiments, and all the while staying safe inside. I saw the movie Gravity. Don't want to go on a spacewalk unless you absolutely have to. But if you are trying to do a dexterous task, you're trying to manipulate things, using the sense of touch and being able to know how you're applying forces, know what your movements are, is really critical. And so without the sense of touch, doing tasks like this takes an expert hours and hours, sometimes years of training to do correctly without the sense of touch. And there are a couple other scenarios that I can give of experts losing the sense of touch. One example is demining or explosive ordnance disposal. If you have a bomb buried in the dirt, you can't always safely defuse it with an autonomous robot or even with a simple teleoperated robot like this one. So another area of work going forward is how do you give someone like a soldier who's in the field and trying to defuse a bomb by manipulating and cutting and snipping in just the right location, the feedback that they need to accomplish this task quickly and safely. And then, as Martha mentioned, one of the applications very close to my heart is medical, in the medical field. And so in teleoperated robot-assisted surgery, which is not science fiction, there are hundreds of thousands of surgical procedures done every year with these type of robots. The surgeon sits at a master console. It almost seems like he or she is playing a video game, manipulating some fancy joysticks, and controlling a remote robot, which in this picture looks really big, but what is actually going inside the patient are instruments that are much tinier than the hands of the clinician. So in this sort of teleoperated scenario, you would like to have a sense of telepresence. If you're the surgeon, you want to act and feel and behave just as if your own hands are directly manipulating the tissue of the patient, and not that you have all of these mechanisms sort of intervening, being an intermediary between you and the patient's tissues. So part of making this a reality, this sense of telepresence, we need the sense of touch, along with the other modalities that you would expect, of course, like vision and sound. So these are just some examples where you don't have to be a patient, you don't have to have lost a limb in order to lose the sense of touch. And none of you, it's possible, maybe none of you have encountered these particular scenarios here, but you all have encountered interacting with your cell phones and your computers and your tablets, right? So this is a famous illustration from Tom Ego that basically describes this is how your computer views you. Well, typically there's no stereo vision, you just have one eye. Often you have stereo audio, so maybe you get two ears, but you interact with it through a single finger. And even then, you touch it. It doesn't touch you back. It doesn't give you any kind of rich haptic feedback that enables you to have the kind of natural interaction that you would have with, say, another person. And so this is the kind of limited way in which computing systems see us. And so all of you are similarly sensory deprived, as some of these experts in these other scenarios I mentioned earlier, even though those are very specialized. The way that computing has become so ubiquitous, we all experience a sort of sensory deprivation when we interact with computational systems. So, one thing you might be wondering is, if touch is so important, why don't we have touch already in these systems? Well, one answer is that it's really technically challenging, and I think some of the progress that we've made that I'll be showing you in some future slides will help you understand what makes it so technically challenging. But another is that we tend to focus a lot on other senses, in particular vision. And so I thought it would be useful to do a comparison between touch and vision, so you can see them not necessarily as competing senses, but rather as dual senses, and understand that there are some things that vision can't provide us, or provides us in a very different way from touch. So let me start with this first one. The first is that sight is centralized. So, of course, we have many rods and cones, and so there's distributed sensing within the eye, but the eyes are pretty much in one location on our body. Whereas touch is distributed. It's all over our bodies. Often we don't always notice that we're being touched. For example, if I always noticed that my clothes were touching my body, that would be pretty disruptive. And so we tend to tune out the sense of touch when it's something that we expect to feel. And we do the same thing with vision as well. But the sensors being centralized versus distributed is something that's very different between vision and touch. Another is that sight is broad. So I can see all of you without having to get closer to you. I have this large-scale sense of what's happening in the room, even though these sensors are in one location. But if I wanted to interact with one of you through the sense of touch, I would have to walk over and poke you in a particular location. You would feel it in one location, and I might feel it in one location on my fingertip. And so this narrowness can help with a kind of specificity of the interaction, but it also creates a technical challenge of how do you stimulate kind of in one location on the body. Similarly, sight passive is maybe an overstatement. If someone does vision research, you know that eyes have saccades, and obviously we explore the world through vision actively. But relatively speaking, my body doesn't really have to move anywhere and exert a lot of energy in order to sense through vision. But in order to sense through touch, I have to be very active. As I mentioned earlier, I'd have to walk across the room and poke you. It requires a lot of physical movement and energy in order to generate a sense of touch. And then finally, sight relative to touch, I would say, could be more cognitive. Part of the reason, of course, the eyes are close to the brain is to allow this as fast as possible an interaction between sight and processing. Touch also requires a lot of processing, but some aspects of touch are very physical, and there are low-level control loops in our body that react to touch of certain types. So, for example, if you've been to the doctor and you're getting your reflexes tested, they might hit you on the knee and you respond. There are responses like that don't reach any kind of cognitive level of decision-making. I don't think I'm going to swing my leg because I just got bonked on the knee. This happens through low-level circuits in our body that can't even be controlled or suppressed usually through cognitive decision-making. So there are aspects of touch which are very kind of reactionary and can't necessarily be controlled cognitively. So, given all these challenges and also the potential dualities between vision and touch, let's just give you a little bit of an introduction to what the technology of haptics does. So probably the easiest way to think about touch, first of all, is how do you create a virtual environment that you can feel through the sense of touch? So let's say you're playing a video game. You have a cursor here represented by this red dot. I want to tap on this teapot. How can we make that feel like a teapot to the user? Well, basically, the user, like my grad student Anne here, would be interacting with a haptic device. There are many different kinds, but here's just one example. It's basically a little desktop robot. These are to scale. She and the robot are in the same scale. And so she basically holds on to the manipulandum, the little end point of the robot, and she can move it around. And as she moves her hand, moves this stylus around in space, this end point is tracked, and then her representation in the virtual world, this red dot, will follow her movements. And then in the virtual environment, if the red dot touches the teapot, we would compute a force. If I push on the teapot, it should push back at me with a certain force in a certain direction. And that force signal is then sent back to this little robot, which has motors in it, which would then apply forces to her hand. And this loop here, the interesting thing about it is it has to run about 1,000 times a second. Unlike images, which usually have to be updated somewhere between 30 and 100 hertz to look smooth, our tactile sensors, our mechanoreceptors embedded in our skin, are extremely sensitive to high-frequency changes. And so just like you might see separate frames in a movie, if it was running too slow, we would feel haptic frames, and things wouldn't feel continuous. They would feel unnecessarily vibratory unless we run this control loop at 1,000 times a second. So that's a technical challenge for us in this field in terms of how do you do the computing of the interaction with what might be a very complex virtual environment with dynamics and all kinds of things happening, and how do you give that feedback to the human in this very, very tight loop. One of the cool things I'll say about haptics is, for me as a haptic designer and a person coming from the field of robotics, is in this virtual environment, like the game designers that were referred to earlier, you kind of get to play God. You get to make that virtual environment be whatever you want. And so this might try to represent the physics of a real teapot, but I could create a teapot that is smaller than a real teapot, that's larger, that's harder, that's softer. Maybe it weighs nothing. Maybe it's extremely heavy. It could pretend it's being made out of different materials. And so as a haptic designer, I get to play God in this virtual environment and basically make it feel however I want, with the only constraint being how fast I can do the computation, and also what is the power of the motors and the sensing on this robotic device that would let me provide that feedback and stimulate the human operator. So that's the limitation. The other main application, and this was most of the examples I gave earlier, is teleoperation, where you're not interacting with the virtual world, but rather you're interacting with a remote robot. And so here, Anne's motions are now being sent as motion commands to the robot, just like a surgeon is sending motion commands to a surgical robot, which is inside the body of the patient. In current clinical practice, these robots are not autonomous. They're following the movements of the surgeon. And then you have to figure out, well, if I touch the environment, I need to have real-world sensors to measure those touch interactions, take those forces, and feed them back to the human operator. So it's similar to a virtual world, but now instead of being able to play God and make up our own physics in that virtual world, we are constrained to sensing what's happening in the real world and providing the appropriate feedback. Not all of the haptic devices are these kind of desktop robots like the one I just showed. And in fact, most of the rest of the presentation will be showing you devices that don't look like that. And these are the things that are newer in the haptics field. So for example, wearable devices that can be at different locations on the body that can give you, for example, vibration feedback and tell you if you want to hit a certain yoga pose, you should move your hand to the left or to the right. You can have wearable systems like this. And feeding these signals back not just through forces that push on the whole arm, but rather just stimulate the skin is a big area of importance in this field right now as we try to make these devices more wearable, cheaper, and more appropriate for consumer applications, not just, say, surgery or astronauts teleoperating robots in space. So with that, I want to give you a few examples of things that are happening in the field of haptics and the kind of results that we can get, going from work that I already mentioned in robot-assisted surgery to fingertip haptics, active surfaces, and some work we're doing in collaboration with the School of Education. So the first one is robot-assisted surgery, which, like I said, is not science fiction. Rather, we've gone from handheld, minimally invasive surgery procedures like this one to robot-assisted procedures where now a robot controls these instruments. And by the way, there's no bloody pictures here. Remove those for this audience. This is artificial tissue, foam and rubber, so if you're the queasy type, it's all fake. In teleoperated robot-assisted surgery, what we're doing is having the motions of the patient-side robot inside the body, following the motions of the surgeon. And so this split screen here shows this quite directly. The important thing to note here is that these two images are not at the same scale. The hand has a scale of about 10 centimeters. The gripper there has a scale of about 1 centimeter. And so you can have about a 10 times reduction in movement, and this kind of Lilliputian shrinking of the surgeon allows them to be more accurate and more dexterous at a scale that they could not have with their own hands. The problem, well, one of the challenges, I would say clinically with these systems, is that we would like to get information from the patient side and feed it back into the master console. So most of these systems that are currently available commercially have some limitations in the types of procedures they can be used for because they don't have haptic feedback. And just as one example of a way that you can provide haptic feedback is to take the motions of the surgeon and the movements of the patient-side robot, and without putting additional sensors on the patient-side robot, because it's very difficult to make them inexpensive and biocompatible and sterilizable, can we look at errors between these movements and estimate if I'm pushing something on something that might be causing differences between the human's motion and the patient-side robot's motion. And that error can then be fed back to the human operator. And this is not something that I can have all of you sit down and try with your own hands. So an example of how this works is done using a visualization. This is a kind of augmented reality bar graph, which is just going up and down, saying how much force is being applied. And we did a comparison with this kinds of feedback between getting this sort of visual display versus pushing directly back on the hands of the surgeon versus not having any extra feedback at all. And in all cases, just getting the natural visual feedback of palpating on the soft tissue and trying to find a hard lump within it. And it turns out that in a case of exploring an environment and trying to detect a hard lump that might represent cancer, even experienced surgeons who have done hundreds of surgical robotic procedures do the best when they get real haptic feedback, which is not yet commercially available. And it turns out this is one of those cases where you can't just replace haptics with vision. This bar graph going up and down might look like a pretty good way to represent haptic information, but it turns out that people don't integrate this sort of visual data so well into a kind of spatial map of tissue properties. And so they do much better when they actually get force feedback to the hand. So another type of haptic device, now which gets away from force feedback of these kind of manipulandum robots that push back on your whole hand, is thinking about how do we just provide information to the fingertips, which might make these devices wearable in the future. And a key component of, I would say, the latest and most interesting types of haptic research have to do with haptic illusions. How do you stimulate the skin alone in ways that make you feel like you're getting whole forces being applied to your hand or to the body? And so our technique is to do a form of skin stretch, where, for example, if you take a pen and you push it onto a surface, you might feel forces in your muscles and your joints, but you also feel local skin deformation on your skin. And so we're asking, what if we just display the part where we deform the skin without having the rest of the forces? Because those other forces require large motors, a grounded robot, and it's not going to be wearable. So we've created these little tactors, we call them, which locally deform the skin, and we can mount them on top of devices or make them wearable, like in this video here, where we're tracking their movement right now with one of these desktop devices. But if this person's finger was over this little red dot, they would feel local skin deformation that would match what they would feel if they were actually pushing on something in the virtual world. All right, and this can be done with teleoperation as well. So here's a teleoperation example. Again, this is like the medical application I just talked about, where we're palpating artificial tissue to try to find hard lumps in it so that we could display to surgeons where a cancerous tissue might be located. So what we really want to do, of course, is make this wearable. And so this is a recent system developed by my grad student, Sam, where you put the device on the finger, and it has what we call 3 degrees of freedom. It moves in shear, like an XY on the surface of the skin, and it moves normally to the skin. And in that way, we can shear the skin and apply normal forces to the skin in a way that would recreate the types of tactile interactions we would have when we directly manipulate objects in the world. So in a minute, it's going to show him picking up objects and interacting with them in a virtual environment. He can have them on multiple fingers. And as he picks up these objects, he feels compression on his fingertips. The interesting thing is that he can very naturally manipulate objects in this virtual world, even though he's not getting any net forces. If he wanted to, he could just squeeze his fingers right through the virtual object. There's nothing preventing his fingers from coming together to touch. But rather, just getting this sort of haptic feedback on the skin is enabling him to do these very natural interactions. All right. We can study questions like in what ways people perceive mass in virtual environments. This is where I'm going to flip through some things really quickly just so you can get some idea of what these devices look like. We also use vibrations, for example, asymmetric vibrations, which don't display a kind of consistent sine wave, but push you harder in one direction than another. And these kinds of vibrations actually compel people to move in certain directions. We do things like add flywheels onto devices that can be holdable, but still create net forces on the hand, and that can cause people to move and feel forces in different directions. And then finally, we've even taken some inspiration from the field of soft robotics, which is using a lot of pneumatics and air pressure type systems in order to be able to display very lightweight wearable devices that are now not just wearable by people, but could even be wearable by objects. So for example, you can put this onto a surface of an object like an ultrasound probe and then guide a clinician in order to move the ultrasound probe as desired. The very last area I want to mention is active surfaces. So this is where we get more into the literal recreation of objects so that you can feel them in whatever way you want. Rather than just having something on your finger stimulating you, can we recreate the object that changes shape and mechanical properties so that you can explore it with your own hand? And this concept goes way back into the 80s and 90s, where people were talking about the concept of digital clay. But we're starting to finally get to the point of novel actuation techniques and sensing that might make this a reality. So this is pretty raw. It's not going to be our dream of the digital object yet, but it might give you a window into where this can go. So going back, originally we had pin arrays. Then people wanted to make these deformable crusts that would change shape. And that's where we are, is to create these deformable crusts. So here's an example video of one of these systems that do this. And I'll tell you about the mechanism as it plays through. So the idea is there's 4 cells here. Each cell has within it coffee grounds. And if we vacuum the air out of these cells, they become very hard. And so the coffee grounds actually jam together when you vacuum it out, and that allows us to change mechanical properties. So it's kind of very off the shelf and cheap, but it works. And there may be more advanced materials and more sophisticated ways to do it, but it allows for very rapid prototyping of these concepts. And then air pressure from below can change the global shape. And so you can see some examples of how this surface can change shape and mechanical properties. All right. So one last example of a different kind of haptic device, and that is haptics for education. So we have, in our laboratory, given hundreds and hundreds of young students tours and allowed them to feel haptic devices. And it's become very clear over the time that the students can't wait to get their hands on these things. I love this video because the students are literally crawling all over each other in order to get their hands on them. And so our goal is to make these devices then as cheap and accessible and even so students can build them themselves in an educational environment so that they can make this connection between the equations of physics that they get to program in a virtual environment and then what they feel. So the students now get to play God with physics and see what's right and what's wrong, and hopefully do this kind of play that John talked about, which would allow them to learn in a very exploratory fashion. And if anybody here is interested in haptics and wants to learn how to build one of these cheap, about $50 haptic devices themselves, you can go to hapkit.stanford.edu, and we've got different versions, and you can download the design you like best, put it together, and then use some of our code to get started. And this is totally enabled by new open source hardware and 3D printing techniques that is opening the door to make this technology accessible to more people. And the last comment I want to make is that I have not yet talked about the social aspects of haptics. And this is a huge open area. These are examples of my graduate students interacting with each other with a nice warm cup of coffee or their dog. And these social interactions of touch are extremely important to people. And so this is a whole new field for haptics, social touch and affective haptics, and how does it make people feel. And that's what I want to leave you with, is that we can now start making the connections between this technology and how people behave, how they learn, how they feel, and how they interact with others. And thank you for your time.